Have you ever stopped to think about the insane drama that's unfolding inside your body, like right now? We're talking trillions of your cells in a constant battle for survival, facing threats and making these life or death decisions every single second. So let's dive into this hidden world and see what happens when our cells get pushed to the limit.
And that's really the big question, isn't it? From something as simple as a lack of oxygen to a huge injury, our cells are constantly dealing with stress. And how they react to that stress? Well, it's fundamental to our health, to disease, and really to life itself. See, every single cell is trying to maintain this really delicate balance. And when it gets hit with stress, it comes to a crossroads. It has a choice to make. It can adapt to the new situation, it can get injured, or it can die. Let's start with its first and smartest line of defense. That state of perfect balance is called homeostasis. You can think of it as the cell's comfort zone, its happy place. It's the ideal operating range. And pretty much every response we're about to talk about is just the cell's attempt to either stay in this state or fight its way back when things go sideways.
Okay, so when the stress is persistent but it's not an immediate knockout punch, the cell's first move is a really clever one. It adapts. It literally changes its structure or its function to find a new steady state, one that can handle this new environment. And it has 4 main tricks up its sleeve to do this.
First up, there's hypertrophy. This is when cells simply get bigger. The classic example, a bodybuilder's muscles. I mean, pumping iron is a form of stress, right? So the muscle cells respond by growing larger to handle that bigger workload. The exact same thing happens to the heart muscle when it has to pump against high blood pressure. Bigger cells, but, and this is key, the same number of cells.
Next, we've got hyperplasia. Now, this isn't about getting bigger, it's about making more. If a tissue is made of cells that are able to divide, they might respond to stress by just multiplying. A really fantastic example is the liver. If you were to remove a piece of it, the remaining cells would start dividing like crazy to regenerate the organ right back to its original size. So let's be clear, hypertrophy is bigger cells, hyperplasia is more cells.
Now, on the flip side of all that growth, there's atrophy. This is where cells actually shrink in size and sometimes in number. Just think about what happens to the muscles in a leg that's been stuck in a cast for 6 weeks. With basically no workload, those muscle cells atrophy from disuse. And on a more serious note, if the blood supply to the brain is reduced in old age, it can cause the brain tissue to atrophy too. And last but not least, we have the most unusual adaptation of all, metaplasia. This is like a complete cellular costume change, where one type of mature cell gets replaced by a totally different type. In a habitual smoker, for example, the delicate, hair-like cells that line the airways can get swapped out for tougher, more rugged cells, kind of like the ones in your skin. Now, these new cells can handle the smoke better, sure, but here's the trade-off. You lose the crucial function of the original cells, which was to clear out mucus. It's a real double-edged sword. But here's the thing. Adaptation can only get you so far. What happens when the stress is just too intense, where the cell can't keep up with the changes? Well, that's when we cross a critical line, moving out of adaptation and into the real danger zone of cell injury. Now, it's super important to understand the injury isn't like a light switch that's just on or off. At first, the injury is reversible. The cell might swell up, its energy production might take a hit, but if you remove that stress, it can bounce back. But if that stress just keeps going, it hits what's called the point of no return. At that point, the damage is irreversible, and the cell is now destined to die. There's no coming back. And that brings us to the first major pathway of cell death. Necrosis. If cell injury is like a building taking some damage, necrosis is that building just collapsing, suddenly, chaotically. It's messy, it's uncontrolled, and it makes a huge mess for the whole neighborhood.
The signs of this chaotic collapse are pretty clear. The cell swells up, its membrane bursts, and it basically spills its guts out into the surrounding tissue. All this cellular debris is a huge red flag for the body, and it triggers a massive inflammatory response. You can think of it like the fire department and ambulances rushing to a disaster site. Necrosis is never, ever a good thing. It's always the result of a serious pathological injury.
It sounds pretty strange to say that, but for the good of the whole organism, there often is a better way. I mean, what if a cell could be taken out of the picture cleanly, without causing a massive scene and damaging all of its neighbors?
Well, the answer lies in our second, much more elegant pathway, apoptosis. This isn't a chaotic collapse at all. This is a carefully planned, meticulously executed demolition. It's basically a form of programmed cell suicide, a tidy exit that avoids all that collateral damage.
So instead of swelling up and bursting, a cell undergoing apoptosis actually shrinks. It neatly packages all its contents into these small, membrane-wrapped fragments called apoptotic bodies. There's no leakage, which means there's no inflammation. It's a quiet, clean removal. And this is brilliant because it shows how apoptosis is often a totally normal, even essential process. It's how our bodies get rid of old cells, how we sculpt our tissues during development, and how we eliminate potentially dangerous cells.
So how does this tidy demolition actually work? Well, it's all run by a special family of enzymes. When the cell gets a death signal, maybe its DNA is damaged beyond repair, it activates the formin enzymes. They then activate the demolition crew, and these guys systematically dismantle the cell from the inside out. Then, finally, cellular cleanup crews swoop in to gobble up the fragments before they can cause any trouble. It's just incredibly efficient.
This comparison just sums it all up perfectly. Just look at the contrast. Necrosis, you've got swelling, bursting membranes, messy leakage, and a ton of inflammation. It's always pathological. Then you have apoptosis, shrinkage, intact membranes, tidy little packages, and zero inflammation. It's often a completely normal physiological process. These are just two profoundly different ways for a cell to die.
So we've gone through this incredible microscopic drama of adaptation, injury, and death. But why does any of this matter to us, really? Because these life and death decisions that our cells are making, well, they are the absolute foundation of our own health and disease.
Our health completely depends on getting the balance of apoptosis just right. If you have too little of it, you're looking at disaster. Cancer cells are, at their core, cells that have forgotten how to die, and that lets them multiply uncontrollably. If your body fails to eliminate immune cells that attack you, you get autoimmune diseases. But on the other hand, too much apoptosis is just as devastating. That's what causes the massive cell loss we see in neurodegenerative diseases like Alzheimer's, or what happens after a heart attack. And that leaves us with a really profound final thought. This stuff isn't just basic biology, it's literally the future of medicine. Understanding these pathways for cell death is opening the door to some incredible new therapies. What if we could tell cancer cells, hey, it's time to undergo apoptosis? Or what if we could prevent neurons from dying in Alzheimer's patients? I mean, if we can truly learn to control how our cells live and die, could we one day master disease and maybe even aging itself?